We now generate the ACF optocorrelation functions and PACF partial optocorrelation function plots to analyze the time series structure. In this section of the programming code, the function par and row equal to C21 arranges the plotting window into 2 rows and 1 column, allowing you to display the 2 plots stacked up vertically. In the main 2 lines to generate the plots, the dashed blue lines, as you've seen on your diagrams, represent the threshold for significant optocorrelation. This threshold is approximately in a range of minus 1.96 over square root of n and plus positive 1.96 over square root of n, where n is the number of observations. For our case, with n equal to 1,000, this corresponds to a 95% confidence interval. Any spikes outside this range are considered statistically significant, meaning those that show meaningful optocorrelation in the ACF and partial optocorrelations in the PACF. The dashed lines in the plots helps to indicate this threshold. Now, looking at the ACF plot, we can see how the series correlated with its lag values. A significant spike at the lag 1 suggests that the MA1 component is present, followed by a gradual decrease. In the PACF plot, there's also a significant spike at the lag 1, which indicates the influence of the AR1 term. Finally, on the screen, you can see par and row equal to C11. This function is going to reset the plotting window to display 1 plot at a time after using a multiple plot layout. Let's move on to other functions. In this case, we're looking at fit ARIMA model. Using opto-ARIMA function, we fit an ARIMA model to stimulate the data. This function tests different combinations of ARI and MA term to find the best fitting model based on several criteria, including the RKA information criterion and Bayesian information criterion. The output from the summary functions provide the estimate coefficients for the AR1 and MA1 terms, along with the important matrix such as the AIC and BIC values. In the ARIMA 101 model, the estimate coefficient for the optoregressive AR and moving average MA components are, as we've seen on the screen, AR1, which is equal to 0.4654 with a standard error of 0.0320. MA1, the coefficient there is 0.6978 with standard error of 0.0260. In this coefficient are close to the 2 values using the stimulations that we set at the beginning in our program. We set the coefficient of AR equal to 0.5, the coefficient of MA equal to 0.7. For the AIC measures the relative quality of statistical model for given dataset. It balances model complexity with the goodness of fit, penalizing model with too many parameters. Lower AIC value indicate a better fitting models. When comparing the multiple models, the model with the smallest AIC values preferred, and it suggested the best trade-off between the fit and complexity. BIC. The BIC is another criterion for model selections like AIC. BIC penalizes models for having too many parameters, but with a stronger penalty for complexity. Lower BIC value indicates a better model. BIC penalizes more complex model more heavily than AIC does. Therefore, when AIC and BIC give different model selections, BIC tends to favor simpler models. Both AIC and BIC help evaluate the balance between model complexity and goodness of fit. However, they differ in how strongly they penalize complexity. AIC tends to select more complex model. It penalizes additional parameter less strongly. BIC is more conservative, favoring simple models, such that it penalizes additional parameters more heavily. In practice, if both criteria point to the same model, it strongly indicates that the model is a good fit. Now let's look at the errors. The first error you're looking at is the root mean square error, RMSE. This error measures the standard deviation of residuals. Predictions errors. Lower RMSE values indicate a better predictive accuracy. As you've seen on the screen, the value of RMSE is equal to 0.9979. It's quite a small number. Now we move on. The other error we have to look at is MAE. MAE stands for mean absolute error. This error measures the average magnitude of the errors in a set of predictions without considering their directions. Like RMSE, lower MAE values indicates a better fit. In conclusion, based on the AIC and BIC values, the ARIMA 101 model strikes a good balance between complexity and fit, with a lower RMSE and MAE values indicate predictive solid performance.